So today's lesson is on rotational equilibrium is what it's called, or we could call it balanced torques is another way of saying it. So rotational equilibrium or balanced torques, you can imagine in this scenario where you and your friend are pushing a table, they're trying to move a table, and you're pushing from opposite sides. So instead of being on the same side, you're pushing on opposite sides. Really, again, it's not really a good way to move the table, it's just a general scenario. But you're pushing with equal forces in opposite directions. Now, according to your friend, your friend says the table is not going to move if you're pushing equal and opposite directions because the conditions for equilibrium are met. But when you push it, instead of moving, it rotates. Okay, so here that scenario brings up a situation where it doesn't move, and that's important because we have equal and opposite forces. It's in equilibrium, static equilibrium, but it does rotate, so it's not meeting what's called translation. It's not meeting what's called rotational equilibrium. So there was no net force on the object. If we drew like a free body diagram, there'd be no net force on the object overall. So it's, again, not going to move, but it is going to rotate based on how they were pushing it because the second condition for equilibrium was not met. We never talked about this concept before. We've drawn free body diagrams in first semester even, and then solved to see like how it's going to change its motion. But we never talked about how it's going to rotate. So it sets up the two different types of equilibriums. Translational equilibrium is where the sum of the forces adds up to zero. And in that case, again, an object could just keep doing what it was doing. If it's moving at constant velocity, it's just going to keep moving at constant velocity. If it's at rest, it's just going to stay at rest. It's not going to change what it's doing. Again, we talked about that when we talked about like Newton's laws, Newton's second law, and so forth, F equals ma. But rotational equilibrium is where the sum of the torques adds up to zero. And so the sum of all the torques on the object must add up to be zero. And then again, it just doesn't rotate. It doesn't change what it's doing, in which case it doesn't rotate in place. Now, obviously, some objects you want to rotate, but not all. So again, depends what the situation is. Now, a lot of times when we're talking about rotational equilibrium, we're talking about balancing things on each side. Here's your friend. You and your friend are on a seesaw together. Your friend Ricky and you are on a seesaw. Ricky is much larger than you are, though. And a good example of this is you have some previous experience with that. How can you guys still seesaw together? And where should you sit so that you can seesaw together and have fun and whatnot on the seesaw and balance? Rest of you know this one? You ever do much seesaw and teeter-totting when you were a kid? A little bit. It's been a while. Yeah. Yes. Ricky has to sit closer to the center of the seesaw, and you have to sit further away. Okay, that's gonna cause you guys to balance, cause the two of you to balance on the seesaw. And again, that's a little bit more fun to balance instead of just one person being up the whole time, right? So again, it's not really much seesawing if the one person is just on the ground and the other person's up. But in that case, you would rotate, you'd be in balanced equilibrium. So are the conditions for equilibrium satisfied? If he sits closer, yes, they are. Why is that? Because the torques are going to balance each other out. Remember that torque in general is force times distance. And it's times sine of theta, but we don't have any angles here, so we don't have to worry about that. And so you, on the left side, have a smaller force but a larger distance. It adds up, let's just say, your force is 2 and your distance is 5, right? Okay, so your torque is adding up to 10, multiplying out to 10. But on the other hand, Ricky's over here has a force of 5 and he has a distance of 2. So again, that multiplies together, gives you a net torque of 10. So you have 10 on the right side, 10 on the left side, and those torques are going to balance each other out from the on the seesaw. Okay, now obviously that problem is just kind of like a thinking problem, but if we want to solve a problem, we need some numbers and so forth. And so, anyways, how to solve a typical torque problem. 1, list what's given to you or find out what's given to you in the problem. 2, draw a torque diagram. Now, this is one of the most important parts of a torque problem, is to actually get yourself a diagram. Because in the last one, we kind of like, we saw a picture of what was going on in the seesaw, and it gives you a good idea of what the situation, like what's actually happening. So it's important to have yourself a diagram to go off of, so you kind of like have a little bit of a visual of where the forces are acting. So label the forces at their locations, label the weights of their objects from their center of gravities, define a pivot point, and then once you have the diagram, you have to determine if the force, all the forces, are producing a clockwise torque or a counterclockwise torque. It really depends on which side of the fulcrum they're on. That sets them positive or negative. So clockwise is negative, counterclockwise is positive, and then again, what we'll do is add up all the torques to see if they add up to 0. If they add up to 0, you're in rotational equilibrium. If they don't add up to 0, you're not. In all these problems, though, we're trying to get the rotational equilibrium to be 0. So you might have to solve for any like unknowns based on, again, saying it's balanced. If it is balanced, solve for the missing value. Okay, now that's the directions for how to do the problem, but let's go ahead and let's actually do some problems. That way you guys get an understanding of how to do some rotational equilibrium problems. Okay, here's basically another teeter-totter situation. And it's just a little bit more drastic. Suppose you are an animal trainer of the circus. You have a very strong, very light wooden plank, and you want to balance yourself with an elephant. So a 6,300 kilogram elephant on one side, and you are going to stand on the other side so that you can seesaw with an elephant. Again, that'd be a pretty cool circus trick, I think, right? Seesawing with an elephant. You just have to have the right tools to do it. So suppose your body has a mass of 50 kilograms, and the elephant's going to stand on one side, 2 meters away from the fulcrum, and you're going to stand how far on the other side of the fulcrum. Okay, so there's a little diagram. I mean, that's obviously a little bit of a cartoon, but it's pretty much a diagram of what's going on. I'll move that up a little bit. Now, we can list what's given to us and draw a diagram, I think, at kind of like the same time, or we can kind of like pull out some information from the problem and then kind of like label it. So gives you the mass of the elephant. We can circle that. We've got the mass of ourselves. We've got the distance the elephant's going to stand. And the question is, how long must the plank be to make it balance if you're standing at the one end? So you're really trying to find a distance. That's all the information we need. Okay, now we have ourselves a diagram, but we kind of like need to label this stuff on the diagram. We have our fulcrum here. That's the triangle portion. And the elephant's going to be standing 2 meters from the end. So we're just going to assume the distance is 2 there, 2 meters. The diagram isn't really quite showing it, but let's just say the elephant has a mass of 6,300 kilograms. But it doesn't. We don't want to label the masses at their locations. We want to label their forces. So, what force is the elephant providing to the teeter-totter seesaw? What do we have to do to that mass? Multiply by gravity. Yes, multiply by gravity. We're going to multiply that one by gravity, so that way we get the force at that point, the weight of the elephant. On the other hand, over here, we've got our mass is 50 kilograms. We're going to do the same thing, multiply that by 9.81. And then, again, our problem is to solve for what is that distance there? What is the distance I have to stand away from the fulcrum to make myself balance with that elephant? Okay, solve for some answers. What's the mass of the elephant? Or sorry, the weight of the elephant. So multiply by gravity. 6,300 times 9.81. Okay. 618. 0.03. And then 50 times 9.81 would be the weight of myself, or 590.5 newtons. Okay, so we've got that. Now, step 3 is to kind of, again, figure out which ones are going to be causing a clockwise rotation and which ones are going to cause a counterclockwise rotation, because that's going to make your torques positive or negative. Again, our triangle here, this the portion here, that's our fulcrum. So is the elephant causing a clockwise or counterclockwise rotation around this fulcrum? Counterclockwise. Yep, counterclockwise. And counterclockwise is positive, so I'm going to leave that force as positive. Okay, myself on the other end. Which way am I causing rotation over here on the other side? Yes. I'm going to cause the teeter-totter to kind of rotate clockwise. And that makes that force a negative force. So we're just going to designate positive or negative there as clockwise and counterclockwise. Now we need to set it all equal to 0 and solve for that distance. And there are different ways of doing this, but it's the way we're going to kind of follow. So the torque, we want it to balance. So the net torque is going to add up to 0. The first force is coming from the elephant, 618.03 times the distance of 2. That's the first torque, and that's positive. Plus the second torque, negative 490.5 times distance 2. We'll just call it distance 2. Okay? So if I add those together, I'm going to get 0 as my final answer. So now I just solve for distance 2, the one variable I'm missing. 618.03 times 2 is 125,606, and that's minus 490.5 d2. That equals 0. I'm going to subtract this to the other side, so that gives me negative 125,606 equals negative 490.5 d2. I'm going to then divide by 490.5. So divide by 490.5. And that gives me a distance 2 of 256 meters. That's how far I would have to stand away from the fulcrum to balance with an elephant. It is. Kind of. Not really. Well, yes, it's final answer for a second. I'm going to go back up to the problem here. So that, again, how far I have to be away from the fulcrum. Obviously, that's a really large distance and not something that you could actually do. What would that be? I mean, that's almost like almost 3 football fields. So, like, probably not going to be possible to necessarily do something like that. The question says, how long must the plank be in order to balance that? So this is not technically your final answer. That's how far away you have to be from the fulcrum, but the plank has to be 2 meters longer than that because the elephant's on the other side for 2 meters. So the plank has to be 256 meters, or 58 meters. That's my final answer. Okay. To answer the question, my plank has to be 258 meters, but I need to stand 256 meters away from it. Okay. Now, again, there are other ways to solve this problem, but this is the way, I normally do them. But what you can also do is you can kind of set your left side equal to your right side and solve it that way too, okay? Because saying that they all add up to 0 is also saying like your left side of the fulcrum is equal to your right side of the fulcrum. And again, it doesn't really matter if you do it that way, okay? Let's look at 2 more problems. Again, this one I've kind of already set up in a way. Again, it's just a diagram. I've given you all the given information, and I already have a diagram of like where the forces are and so forth. So we just kind of like need to figure out which ones are causing clockwise rotation, which ones are causing counterclockwise rotation, and then solve for the missing unknown value. Okay, we've got ourselves a 2-meter board is what it basically is. It's a 2-meter board, and the pivot point or the fulcrum is right here in the middle at 100 centimeters, right in the middle. I hang 8 newtons from the board on the left side, 50 centimeters away from the pivot point. And I have another force, 175 centimeters over here on this side as well. But I don't know what that force is. So that's what I'm trying to solve for, is how much it's balancing. How much is that force? Okay. Now, what this problem, we want to, again, kind of remember that, and the way it's set up is really to get you to focus that the distance in the problem are not the distances like given to you on the beam. It's the distances from the pivot point. So if this mass or this weight here is hanging at 50 centimeters, how far is it away from the pivot point? The pivot point's at 100. This is at 50. So the distance there is 50 centimeters or 0.5 meters, which would be what we want to do there. Now, the other one, the pivot point is at 100, and then this force is at 175 centimeters. How far away from the pivot point is that? 0.75 meters. Good. Now, what a lot of people do, though, in a lot of these problems is, in this case, they would just put 50, which it actually does work out to be the same answer, but people would put the distance as 175 over here. And again, that's not the case. You're always measuring the distances from the pivot point, and that's an important part when you're doing these problems. Okay, now we can solve the problem again. 0 equals 8 newtons. Is that causing a clockwise rotation or a counterclockwise rotation? Moving it like this way. Is that clockwise or counterclockwise? Yep, and so we leave that one as positive. Is this force going to be, is this force going to come out to be positive or negative is the question, I guess. Clockwise or counterclockwise? Clockwise. So when we do the math, that force will come out to be negative. Yeah. Well, I guess your question is, how do you know if it's going to be a clockwise? So counterclockwise is always positive. Clockwise is going to be negative. You have to look at where the pivot is, where the fulcrum is, and then see which way the force is going. And the force is going to, and this force is causing it to rotate this direction, which would be counterclockwise. This force, since it's on the right side of the pivot, is causing it to rotate clockwise, which we would call negative. The force is down, but the force is causing this to rotate. Now, if I have a force over here on the end, it's still on the right side, but that's causing it to rotate that way, and that would be counterclockwise, which would be positive. So, like, what? Sure, why not? Okay. Got myself a meter stick on my desk. Okay, it's balanced in the middle for the most part. Again, if I kind of push down on this side, it causes it to rotate this way, which from your perspective would be counterclockwise. So that would be considered a positive torque. If I push it up on this side, it causes it to rotate this way, which would be clockwise, which we would consider a negative. It's just, again, because it's not like moving up, down, left, or right, which again, up is positive, down is negative, right's positive, left is negative. Because of that, we have to designate a direction as being positive or negative, and it's not really moving in a direction; it's moving in a like a rotation, and we just consider one of them to be positive rotating and one to be negative rotating. Counterclockwise is positive. Yeah, that's a good question. Why did they choose counterclockwise as being the positive direction? I don't know. Just you have to designate one as being positive, one as being negative, and counterclockwise is not the way a clock moves. Counterclockwise is not the way the clock moves. So, oops, I didn't solve the problem. We didn't solve the problem. Okay, so torques add up to 0. The first force I come to is the left one on the left. It's 8 newtons, positive, times the distance of 0.5, plus the force number 2, which we don't know that force, we do know the distance is 0.75 meters, though. Okay, now, I guess the question, is that force going to be more or less? We do know that. We can figure that one out. Is that force going to be more or less? It's further away from the fulcrum. It's going to be less. That force has to be less to get it to balance. Okay, so 8 times 0.5 is 4, plus 0.75 F2, and we'd subtract the force equals 0. Subtract that to the other side, so you have negative 4 equals 0.75 F2, and then we would divide 4 by 0.75. Gives us a force 2 of negative 5.3. That'd be newtons. And again, it comes out to be negative because it's moving clockwise. It's a clockwise rotation. Last problem. Last problem. Now, this one's, I think, a little bit harder. And this would be one where we come into the case where you can't like set your left side equal to your right side because everything's on the right side. So again, like this makes sense, Isaac. Kind of like what? So this is again why I kind of just like always set it always equal to 0, but it is possible to set your it equal to each other. Like you'd have to have the clockwise rotations equaling the counterclockwise rotations. So you just kind of have to think about what you're doing a little bit more as versus like the left and the right. So what would the upward force here at the end be is the question. We have a board. Our pivot point is all the way on the left side. And we have 3 forces on this board. We have force number 1 here, 270. Force number 2 is coming from the board itself, the center of gravity of the board, 1080. And we're force number 3. And force number 3 is going to cause it to move up there, it's going to balance everything out, if that makes sense. So what is that last force? The torques all add up to 0. The first 2 torques are causing a clockwise rotation around the pivot point. So these 2 forces are going to be negative. Does that make sense? Okay, clockwise is negative. So the first force we come to is negative 270 newtons. And the distance away from the fulcrum is 12 meters. The second force we come to is negative 1080. And that one is 24 meters from the fulcrum. And the third force we come to, the one that we're missing, is the one we don't know, but that one is 48 meters away from the fulcrum. That one's going to come out to be positive because it's, again, moving in a counterclockwise direction, and we just have to figure out what that last one is. Okay, so now we come in here and we solve some of this. 270 times 12 plus 1080 times 24. So that comes out to be negative 29160, and that's plus 48 F3, force 3. That all equals 0. I'm going to add that to the other side, so now that becomes 29160 equals 48 F3, and I'm going to divide that by 48 then to get my answer. 607.5 newtons is F3. That's my final answer. Sure. Yeah, okay. Yeah, I guess I get what you're saying. There's nothing on the left side. So it's all the right side stuff equal to the left side stuff. Yeah. Yeah. Which, sure. I'll think about that one. In this one you did, though. You can't do this one without thinking about the negative. Sure. However you want to think about it, I'm fine if you do the problems that way. Yep. Okay. So hopefully this makes a little bit of sense to you, and hopefully you know how to do some balanced torque problems.